We've talked about energy a little bit already. We said that energy is anything that has the capacity to do work, and that work is a force acting over a distance. You know, like raising up this dry erase marker. By lifting it up against the force of gravity, I have done work on the marker. And heat is a flow of energy caused by a difference in temperature. These are concepts that we introduced a little earlier in this semester. Heat always flows from a higher temperature to a lower temperature. Energy, in the form of heat and other forms as well, can be exchanged between objects through contact. An example is through collisions, and we just got done talking about the kinetic molecular theory of gases and about how when two gas particles collide, there can be an exchange of energy, but they collide in an elastic way, and so there's no energy that's lost from kinetic energy. It's all conserved as kinetic energy. But in the macroscopic world, you know, you have a large object run into a brick wall, there's going to be a loss of kinetic energy. The energy isn't lost, but it's transferred into heat. Some of that heat energy is transferred to the wall. So we can think of energy as a quantity that something can possess. In some situations, it's helpful to think of energy like we think of money. I can have money, and I can give money to you, or you can give money to me. It can be transferred back and forth, but the money always exists. And we can change the money from bills into coins, or we can change it from dollars into kroner, or all kinds of different things. So energy is this quantity that it can be possessed. Heat and work are ways that energy can be transferred or exchanged. So energy can move out of an object or into it, and so energy has a directionality. Just like money. When money leaves me, I feel negative about that. When someone gives me money and money comes into my wallet, I have positive feelings about that. So we'll relate that to the transfer of energy as well. Next slide here. So classification of energy. We classify energy into different types, and some of this we've already looked at. Kinetic energy, we should already know the energy of motion. So over here, we've got a picture of a pool table, and we've got the cue ball here moving towards this purple ball. This ball has kinetic energy because of its motion. And we looked yesterday and saw that kinetic energy is 1/2 the mass times the velocity squared. So it's related to the speed at which the object is moving, but also to the mass. This ball over here is sitting still, and so its kinetic energy is very, very low. Then we have thermal energy. This is the energy that's associated with temperature. This can be very confusing. Thermal energy and heat are not the same thing. Okay? Heat gets transferred, is this flow of energy from one thing to another, but the actual energy, that thing that can be possessed, is thermal energy. Thermal energy is actually a form of kinetic energy. Everything has a certain amount of thermal energy. The thermal energy being kinetic energy has to do with the particles moving. So if you take, let's say, a pot of water, it's room temperature water, you stick it on the stove and you heat it up. Is the water like traveling across the kitchen? No, it seems like it's just sitting still on the stove, right? But as you put energy into it by turning on the stove, the particles within the liquid are moving faster. And that is how thermal energy is actually a form of kinetic energy. So when this cue ball hits this ball, what happens as they collide is there's a transfer of energy. The cue ball transfers its kinetic energy to the purple ball. And this is a process of doing work. Now this energy has been transferred. Now this ball goes off and that ball sits still. There was a transfer of energy. Yes?
When those balls come to rest, they stop, they hit each other and they stop.
Mm-hmm.
What happens to the energy? They just hold it until it's time to...
So with pool balls, there is friction as they roll across the table. And that's why they do not keep moving indefinitely. No matter how hard you hit a cue ball or a pool ball, it will eventually come to rest, right? You can hit it really hard and get it to bounce back and forth a couple times. As it is rolling, there is friction. The friction causes a loss of some of that kinetic energy to heat. It's not noticeable to us. We can't detect that small amount of heat. But that kinetic energy of motion is going somewhere as the ball slows down. And most of that is going into heat. Now, with a gas, the gas is traveling through empty space, the gas molecules. There is no friction for those gas molecules. And that's why a gas molecule will continue in motion indefinitely until it runs into something. And then depending on how it runs into that something, it can slow down and transfer some of its kinetic energy to the other, or it can retain all of its kinetic energy and its velocity. When gas molecules collide, it's completely elastic, meaning all of the kinetic energy is conserved. That's not the case with pool balls. It's close. It's our best example of it, but there is some loss of kinetic energy. Does that help? Yeah. This stuff is, kind of weird, right? And they probably didn't go into much detailing about this in a previous chemistry class that you had. So I really, really want you to ask me questions. Because, I have to kind of level out. I mean, I could just skim over it really fast, or I could spend hours and hours and hours, but we have to get through in a certain amount of time. So I'm going to kind of go at a middle level, and if you're not understanding, please ask me, and I will take the time if there's questions. Okay, so potential energy is energy that's stored. This can be due to composition or position. This dry erase marker up here has potential energy because if I let go of it, it falls. The potential energy gets transferred into the kinetic energy. It hits the table, the kinetic energy gets transferred into thermal energy. That's energy of position, like in this illustration, dropping the ball. There's a gravitational pull on this ball, and so when we release the ball, it falls and it has kinetic energy. Chemical energy is a form of potential energy, but it's not due to position above the Earth. It's due to the relative positions and the interactions of the electrons and the nuclei within the atoms and molecules. It has to do with energy that is stored within chemical bonds and the interactions between the particles in an atom or a molecule. And chemical energy, of course, is what we're primarily interested in chemistry. We don't do a lot of dropping of objects intentionally. We do drop things, though, don't we? We've already broken a fair amount of glassware, which is fine. Glass breaks. Okay, so flow chart, kind of summarizing. Energy is the capacity to do work. We've got kinetic energy due to motion, potential energy due to position or composition. Subgroup of potential energy is chemical energy. Subgroup of kinetic energy is thermal energy, energy associated with temperature. If you're really interested in energy, you should go study physics, because they get way more into this. Here are some other forms of energy. There's electrical energy. Okay, if you've ever gotten shocked from an outlet or something, you know that there's energy in there, right? And it hurts. That is kinetic energy that is associated with the flow of electrical charge. Heat or thermal energy is We've talked about that. The kinetic energy associated with molecular motion. There's light energy or radiant energy. This has to do with energy transitions in an atom. Nuclear energy is potential energy that's stored in the nucleus of atoms. You know, we're all familiar with the atomic bombs that were dropped on Japan during World War II. Tremendous, tremendous amounts of energy. And that comes from splitting apart the nucleus of atoms. There's an incredible amount of energy stored inside the nuclei. Chemical energy. Potential energy due to structure of atoms, the attachment between the atoms positions relative to each other, or the molecules' relative positions. So these are all different types of energy. Much of this stuff is review, but we need to go over it again. Law of conservation of energy. Energy can't be created or destroyed, but it can be transferred from one form to another and from one object to another. But the total amount of energy present at the beginning must be present at the end. Now, sometimes it appears that energy is lost, but that's just because we haven't examined it closely enough. Here's an illustration of a woman pressing a ball down on a spring. And so this is a mechanical potential energy, right? Pressing down on the spring, she's putting energy into the spring, and when you release that, the spring uncoils and shoots the ball up in the air. There's no loss of energy in that transformation. So when we talk about energy, we need to carefully define where the energy is coming from and where it's going. And we typically do this by talking about a system and a surroundings. So the system, you can define that in any way that you want. We could define the system as things happening within this room. You could define the system as something happening within your crucible. You spill water on your arm. You could talk about the system being the water that is spilled on your arm and what's happening to it as it evaporates. So we define the system. The surroundings are the rest of the universe. So the surroundings are just huge, right? It's everything else. So we've got the system, whatever we're looking at, and the surroundings. And so we talk about the energy exchange between that thing that we're interested in, the system, and everything else around it. So in terms of system and surroundings, we talk about conservation of energy, meaning that whatever is gained or lost by the system has to be equal and opposite of what is gained or lost by the surroundings. So here, if we have a little energy meter here, here's our system energy gauge, and it's half full. The surroundings are a quarter full. And there is some sort of energy transfer. When the energy transfer occurs, all the energy that's lost from the system was transferred to the surroundings. Now, we're not saying anything about what form of energy that is, but just that the energy transfer, there's nothing that's lost. So whatever's lost by the system is gained by the surroundings and vice versa. Well, energy is something that is measurable, and so of course we have to have units for energy. Here's our relationship between kinetic energy, mass, and velocity. So kinetic energy is 1/2 the mass times the velocity squared. The SI unit of energy is the joule. This is a kind of a funny font. That's a J. And it's a French word. It's pronounced jewel, just like you would have a jewel on a crown or something. And the unit joule comes directly from this equation. A joule is a kilogram meter squared per second squared, and we had a little peek of that yesterday. Mass, and this is velocity, meters per second squared. So joule is a unit of energy. Another way to think of it as a definition is the energy that's needed to move a 1 kilogram mass a distance of 1 meter. So a kilogram is about 2 pounds. So if you take 2 pounds and you push it for a meter, that's a joule of energy. Bless you. Newton comes in here as well. We're not going to do much with newtons. But if we factored meter out of this, we get kilogram meter per second squared, and that's the unit Newton, which is a unit of force. Remember, force times, no, never mind, that was something else. Getting my physics mixed up. Scratch that. Okay, calorie is another unit. This is a unit of energy that you're probably familiar with, although this is calorie with a lowercase c. A calorie is defined as the energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And these are both energy units, so there's a relationship between them. A calorie is exactly equal to 4.184 joules. So that's exact. Those digits aren't going to figure out in your significant figures. So that's one that you could ignore the sig figs on. Kilocalorie, these are metric units. We can apply metric prefixes to them. We can have a kilojoule, we can have a kilocalorie. Kilo means 1,000, so a kilocalorie is the energy needed to raise 1,000 grams of water 1 degree Celsius. What we're familiar with as a food calorie is calorie with a capital C, which most of the time we will avoid using in chemistry class, but it could show up in a couple word problems. The food calorie is actually equal to a kilocalorie. So, you know, if your Tic Tac has 1 calorie in it, it's really 1 kilocalorie. It's the amount of energy needed to heat 1,000 grams of water 1 degree Celsius. There are many other units of energy. One of them is the kilowatt hour. That's what they measure, what the power company measures for your electricity. And here's some relationships between these. Can't see that, it's too small. This is just kind of to help you get a size, you know, a grasp for how big these units are. Think about the amount of energy used by a human body running 1 mile. So that's 100 dietary calories, 0.12 kilowatt hours. So we see that joules and calories are much smaller. So that's just for general interest.